Okay, very quickly, if we have the system, let's say 2x1 plus 3x2 equals 12, and 4x1 plus 6x2 equals 24, then looking at this as a system, if we subtract twice the first row from the second, we end up with 2x1 plus 3x2 equals 12, and 0 equals 0. So this system of two equations reduces down to essentially one equation, which could then be written x1 plus 3 halves x2 equals 6. If you let x2 and 0 equals 0, of course, and let x2 equal t, because x2 could be regarded as your free variable. x1 could be free also, but meaning x2 could take any value at all, and any real number value, and you get a value for x1. Well, if x2 is t, then x1 equals 6 minus 3 halves t, so that the vector x1, x2 equals 6 minus 3 halves t, t. x1 equals this, and x2, as we said here, is t. This equals the vector 6, 0 plus t times the vector negative 3 halves 1. And let's be sure that the cameras get all of that. Okay, so this means then in x1, x2 space, that the vector negative 3 halves 1 is here. Okay, there's your vector negative 3 halves 1. And your vector 6, 0 is here. T times your vector negative 3 halves 1 is going to give you a vector that's longer or shorter than 3 halves 1 by factor t, and maybe on the other side of the origin if t happens to be negative. So the tips of all the vectors that you get if you multiply negative 3 halves 1 by t are going to lie along a straight line. Try to make that line straight, but okay. A straight line parallel to t through the origin. The solutions of the equation are displaced by the vector 6, 0 from the vector t times negative 3 halves 1, which means you take any point on this line and it represents, that point is associated with a vector from the origin to that point, and you displace by the vector 6, 0. Well, I'm not doing that very well, but when you do that, you end up with the tips of these vectors lying along a straight line. I didn't do a great job of keeping things consistent here, but there we have it. The points on this straight line are the solutions, or represent the solutions of our system. Meaning that any vector from the
Listen to music offline. YouTube Music Premium.
and I just realized we have background music here. Hopefully it isn't obscuring anything, but I'm going to pause this, and hopefully that was an enhancement and not a distraction. But okay. Okay, so here are the solutions of our system. Meaning, again, a solution of the system can be thought of as a point in the plane. You take the coordinates of this point, whatever x1 happens to be here, and whatever x2 happens to be for a given point. Okay, the coordinates x1 and x2 plugged in to this system give you a solution. Now we associate that with the vector, and I probably should use a different color for this vector because green and yellow end up looking very similar. Okay, so this vector represents one solution. Okay, a vector here would represent another solution. A vector here would represent another solution. So the purple vectors represent solutions of the system. Now, what about this orange line? Okay, hang on a minute. Dropped a critical piece of chalk. This is down to a pretty short piece. Okay, the orange line, which is just t times negative 3/2 1 for all values of t, represents solutions of the homogeneous system and the homogeneous system here is 2x1 plus 3x2 equals 0, 4x1 plus 6x2 equals 0. Clearly, if we reduce this system, we get x1 plus 3/2 x2 equals 0. Because we have zeros here and here, we end up with zeros here and here, zeros here and here. Meaning that this vector is the vector 0, 0 instead of 6, 0 if we're doing the homogeneous system, so that we just have t times negative 3/2 1. So this is the solution to the homogeneous system. So there are our solutions to the homogeneous system. The row space of the matrix, well, let's look at the system again. Okay, our system is, and just making sure that we got focus on everything. Well, I don't want to write over here because sometimes Zoom blurs things over here for some reason, even though it looks very clear on my screen. So let's come over here. Okay, well, the system can be written as a matrix, matrix equation 2, 3, 4, 6 times x1, x2 equals 12, 24. Okay, this is a matrix of the equation A, x equals B. The matrix reduces to the matrix 1, 3/2, 0, 0. So the row space is spanned by the vector in the row, but I'm going to write it as a column vector. It's not a column, it's a row, but since we're representing our vectors in x1, x2 space by columns, I'll write it as a column vector. Okay, that's 1, 3/2. Meaning the row space is the set of vectors, and I'm going to be a little sloppy with calculation. We'll say S times 1, 3/2. I'll go right and set the set vectors S times 1, 3/2 such that negative infinity less than or equal to S less than or equal to infinity. And that's a bad infinity there, but hopefully that's readable. So the row space is this set, and what's that set? Well, if we graph that in x1, x2 space, the vector 1, 3/2, we come out 1 unit here and up 3/2 here. So here's the vector 1, 3/2, and then here's the vector. Well, here's the set of vectors that you get when you multiply this vector by all real numbers. This is a straight line, and this is the row space of this matrix. Well, the null space of this matrix is the set of vectors that map to 0, the set of vectors write it AX equals 0 in matrix notation, and that would be the set 2, 3, 4, 6, x1, x2 equals 0, 0, and that, which you can verify, I'm not going to go through all the details, is the set, well, color coded if I get a hold of the chalk, that's the set of vectors t times negative 3 halves 1. Okay, so it's the set of these vectors such that negative infinities, getting hard to write infinities down here, less than or equal to t, less than or equal to infinity. Maybe badly written. So what does this look like on our picture? Well, this set we've already got right here. It's the solutions of your homogeneous system, and that's your null space. And now we've got the row space. Well, the row space comes over 1 and up 3 halves. So here's the vector 1, 3 halves. And here's your row space. Okay, the vector really is over the line. Didn't quite get that right. So here's your row space. This whole line, it's the span of this vector, the vector 1, 3 halves, so this is the row space, this is the row space, and the vector here is the vector 1, 3 halves. Okay, this vector. We can easily verify that the vector here is perpendicular to this vector. And that's always got to happen. Your row space always has to be perpendicular to your null space. To see that that's so, what's the slope of this line? Well, the rise is 3 halves, the run is 1. So the slope is 3 halves. What's the slope of this line? Well, rise is 1, the run is negative 3 halves. So I'm going to take this away because we understand how this works. The slope is 3 halves divided by 1, which is 3 halves. That's your slope of the row space. The slope of your null space is rise divided by run. The rise is 1 divided by negative 3 halves, and that's negative 2/3. And what we have here is negative reciprocal slopes. And negative reciprocal slopes imply perpendicular lines. I'll write this for perpendicular because I don't want to write out the whole word, among other things. It takes longer, so you have to sit there watching me longer. Okay, negative reciprocal slopes imply perpendicular lines here and here. So your null space is perpendicular to your row space. That E isn't going to work, is it? Anyhow, it's not row space O, it's row space. Okay? Null space is perpendicular to row space. Another big thing, and I should have another. Here we go. Yep. Let me just get it out. The trigonometry of that operation is really pretty interesting, isn't it? Think about it. Okay, and what is this? Looks like I need to go after the cobwebs. Okay. So, summary, and one additional comment. Okay. Null space is perpendicular to row space. Null space is the span of the vector negative 3/2 1, and that span, since you've only got one vector here, its basis is negative 3/2 1. Its dimension is 1. Row space is this, has dimension 1. Matrix is A equals 2, 3, 4, 6, which reduces to 1, 3/2, 0, 0. Row space has dimension 1, and the null space dimension, I'll write it out, dimension 1. Matrix is n by n, with n equal to 2. Okay, the dimension of your row space is what we call the rank. the null space has dimension 1. We call that the nullity. And the rank plus the nullity is 1 plus 1, which equals n, which is 2. All these come out of the reduced matrix. Everything that we say here comes out of the reduced matrix. The picture is the picture. Null space, row space perpendicular to the null space. This is always true. Okay? What's always so? This is always so, and this is always so. Null space is always, for any matrix, perpendicular to row space. Or, as we'll see, for spaces where perpendicularity doesn't have any real meaning, like polynomial spaces Pn, or matrix spaces, M, n by n, m by n matrices, you don't have a concept of orthogonality. In Euclidean spaces, R1, R2, R3, R4, so forth, Rn, we do have perpendicularity, but we don't always have it. Okay, so these two things are always true for any matrix. These things here are specific to the 2 by 2 matrix, any 2 by 2 matrix that reduces down to a matrix with one row of zeros. Because if you have one row of zeros, you have one non-zero row, that's rank 1. And you have 0 row, 1 0 row, that means your nullity is 1. Okay. That's the simplest overall picture I can give you of row space and null space. Now I'm going to go on and talk about what happens if you have like a 2 by 3 matrix.